In the previous video for the NeoPixel circuit design, I discussed the block diagram of the overall circuit design. And just to review, basically, to make the NeoPixel driver circuit, you need master clock that operates at 800 kilohertz with a relatively long duty cycle. Comparatively, and basically that clock controls four things, and basically the D flip-flop synchronizes everything. The data comes in to the data input of the D flip-flop. The clock triggers the flip-flop, and you either get a Q or a Q bar, inverted Q. So if the data in is a 1, you get a 1 here. If the data is a 0, you get a 1 here. And so each of those goes into an AND gate, and you get an AND operation that gets performed between a high pulse, a monostable high pulse that's about 800 nanoseconds long, and the clock also triggers a low monostable pulse of about 450 nanoseconds long. Each of those go into the corresponding AND gates. If the output of this is a 0, the low pulse is ANDed with the Q bar output of the flip-flop. Similarly, if the output is a 1, you'll get a 1 at the Q output, and you'll get a high pulse that's ANDed with the D flip-flop output. Either of those, either a 0 or a 1, a high pulse or a low pulse, goes through an OR gate, and then that gets output to the NeoPixels. At the same time as this entire process is going on, the clock is also triggering a counter circuit, and the counter is counting up to a value of the total number of NeoPixels times 24 bits per NeoPixel. Since we have to clock in a total of that counter counts up to that value. Once it reaches that value, it triggers another monostable generator, pulse generator, that has to trigger a low pulse of greater than 250 microseconds to stop the clock. It basically resets the clock. It stops it. And when it stops it, it allows the NeoPixels to latch the data that you just put into them. At the same time, that pulse we have to find a way to reset that counter so it can start counting fresh the second the master clock starts counting again. And this is our overall block diagram for the circuit design. And so now today I'm going to talk about how to implement that in the actual circuit. And so in order to do that, the first step is to get a master clock. So the master clock is you can use a crystal oscillator. In my case, I used a 555 timer. So the 555 timer. Let's talk about the 555 timer. For those people who don't know how to use a 555 timer, this is the overall the circuit for a 555 timer. Now keep in mind, I used a TLC 555 timer, not an NE 555. So the difference is the NE 555 timer is not so good at generating very rapid pulses. It sort of reaches its peak ability to oscillate at around 200, 300 kilohertz. I think I got it up to 400 kilohertz at one point. So I couldn't generate a signal fast enough with an NE 555 timer. So the TLC 555 is the same thing, but it's a CMOS version of the 555 timer. And so it can go faster. It can clock up to 2.1 kilohertz or 2.1 megahertz, according to the data sheet. And you could use smaller components with it. So to start the process with the clock, I got a 555 timer. I'm gonna keep I'm gonna redraw the chip here, and this is pin 1, 2, 3, 4, 5, 6, 7, and 8. And so the reset pin is pin 4. This pin goes to VCC. This pin goes to ground. So what I did here was the reset pin I had put through a pulled high through a 20K resistor, and that will prevent the clock from just resetting spontaneously. You want it to reset when you put a low pulse in here, and that's for that later reset signal that is coming later. So the way to wire this in astable mode, you basically have to put pin 2 through a capacitor to ground. I used a 1 nanofarad capacitor, and you connect a resistor has to go here. This is a 100 ohm resistor, and this is a 200 ohm resistor. And I also added a 1K potentiometer, such that, and this all goes to VCC. I would be able to adjust the timing, make fine tuning of the timing here. But if you just put these values in for your astable mode, it will give you a clock frequency which is 0.693 times R1, which is 200 ohms, plus 2 R2. This is the formula for calculating the frequency of a 555 timer, and that should equal, and this is the total period, and 1 over this is the frequency, and that should give you a frequency of about 800 kilohertz. All right, so that is our 555 timer. So the output of this 555 is going to continue with our block diagram. We'll bring that back here. So now we have to get the flip-flop, the monostables, and the counter. So let's start with the easy part, which is the counter. So I I used CD4017 chips for counters. I had an abundance of them from a previous project, so I kept those. I kept those around, so I had 4 of them. And the way the CD4017 works, and here is the pinout of the CD4017, and this is basically a decade counter. It has all of these pins, and so what I did was I took 4 of them, and I arranged them side by side. And the way these chips work is I had the VCC for all of these, ground, and ground. Okay. Then the reset signal, since to reset these, it requires a low pulse, a high pulse at the reset. I tied the reset. It requires a high pulse to reset it. So I tied the reset to ground using a fairly large resistor. I used a 20K here. And I tied all of these resets together. Okay, then this went to the clock pin. I'll write that in here. The carry out went to the next clock pin. Carry out going to the next clock pin, and carry out going to the next clock pin. Okay, this is the carry out. Carry out. This carry out was not necessary. Then, and obviously the other thing that needs to be connected on all these is the clock enable. In order for the clock to be enabled at any time, it needs to be pulled low. And so I just hardwired all of the clock enables to low. And all of these were connected together and connected to ground. And that enabled the clocks. So now, these pins here, shown here, are the values of the pins. So this is the ones digit, this is the tens digit, this is the hundredths digit, and this is the thousands digit. So in my case, we need to count to a value of 24 bits times the number of neopixels, n neopixels. And in my case, I had my n was equal to 144 neopixels. And so I needed this circuit to count to 24 times 144, which is 3,456. And so the pin corresponding to 3,000. And the pin corresponding to 4, which is over here somewhere. And the pin corresponding to 5, which is here. and the pin corresponding to 6, which is the fifth pin 5. And I basically took these outputs. The outputs go high when it reaches that count. And I connected them. Well, I didn't connect them together, but I connected them. Disregard that. I connected each of these to an AND gate, and each of these to an AND gate, and then the outputs of these I connected to another AND gate. So the AND gate I used. I used transistors for it at first, but that didn't work out as well for a 4-input AND gate. So the way a quad input AND gate works is, here's the circuit or the pinout of a 74HC08, which is a quad input or a quad AND gate. It has 4 AND gates on one chip. If this is the notch of the chip, pin 1 is here, pin 16 is here, and the way this chip works is your A is your first input, your B is your second input, and your Y is your output of that. So input 1 of AND, input 2 of AND, and so because this chip has 4 AND gates on it, and it looks like this when it's running, I use 3 of them to create this. So every time the counters, as they are arranged, reach a number of 3,456, when it reaches 3,400, this AND gate will go on and stay on until this one, these two counters reach a value of 56. And this AND gate will go on, and then when it's 3,456, this AND gate will go on, and the output of the AND gate goes to a monostable signal generator, and the monostable signal generator that I needed it to generate a signal of 250 microseconds in length, and it needs to be a low signal in order to reset the master clock or to stop the master clock, because the master clock is tied to VCC here to keep it from resetting. All we have to do is get the monostable to trigger that clock. So how to generate a monostable signal? I used another 555 timer. So another TLC 555 timer. Basically, the way to use the TLC 555 in monostable mode, here once again is the pinout for this. Here is the chip once again. So VCC, ground. This is pin 2, which is the trigger. This is the reset, which is basically tied to VCC. This is the output. And the way this works is this time you're not connecting the pin 7 and pin 6 together through a resistor. You're going to VCC, and This goes to through a capacitor to ground. Okay, and pin 5 is not connected. So in order to generate monostable pulse with this 555 timer, you need to get it to generate a signal of at least 250 microseconds. I think I actually used a 3.3K resistor here. So yeah, this is a 3.3K resistor and 0.1 microfarad capacitor. When I put the two of them together, I got a signal of about 3.4-ish microseconds, 340-ish microseconds. 340 microseconds is all you need to do is this value. You don't want it to be too long because then it just slows down the refresh rate of everything. But you want it to be more than about 250 microseconds and to allow the clock to latch, to allow the neopixels to latch. The only problem with with this circuit is in order to trigger the 555 timer, you need to provide a low pulse for the trigger in order to trigger the monostable to generate an output. And so in order to generate that output, what I did was I put it through an inverter. And that triggered the reset pulse of the 555 timer. Once the value of this AND gate reached 1, because this was a positive value that comes out of here. Once that, and in my case, I didn't use an inverter chip. I just used a inverter in the form of a transistor inverter, which is basically, it's basically a 1K VCC. This is the output. The input is 2K resistor, and this is the input. And the output is, and this just goes to ground. And so this is a transistor inverter or NOT gate. I've used these in my circuits before and they work out pretty well. I just didn't have a inverter chip at the time. So in any case, this output, however, is also a high pulse. It's a 250 microsecond high pulse. So what I did with this is I put it through another transistor-based inverter, and that results in exactly what we need, which is a 250 microsecond low pulse. That 250 microsecond low pulse is what I sent to the clock here at pin 4. And what that does is it basically stopped the clock for precisely 250 microseconds. And it only stops after this count reaches 3,456, which is the total number of bits entered into the neopixels. In addition, we want to be able to reset the counters. So the counter reset, which is here, it's currently pulled low to prevent it from resetting during the count. This requires a high signal in order to reset. So what I did here was I took the high reset signal, which comes out of the 555 the monostable 555 timer, and I brought that before inversion to, from here all the way up to the reset pin of the 555 timer. All these reset pins are cross-connected, and so it resets all of them when this happens. And so every time this the count reached 3,456, the monostable 555 timer would reset the counters and would stop the clock. And that's how to generate the counter circuit. We'll talk about the rest of the circuit in the next video. Thanks for watching.